So we're transitioning from systems of equations. We've done those with both 2 equations and 2 variables to now 3 equations and 3 variables. So now we're transitioning to systems of inequalities. And we're only going to do this for 2 inequalities with 2 variables. Okay. Recall, last unit we looked at just graphing a linear inequality. You draw the line, that's called the boundary line, and then you use a test point to decide which side of the line you should shade, right? And the shaded region is your solution. So for a system of inequalities, now we're just bringing 2 of these together, and we're going to look for the common points that they share, which would be the overlap of their shaded region. Okay? All right, so I kind of already wrote that out here. Solving a system of inequalities requires finding all common solution points. So you will be looking for the overlap of the shaded regions. Okay, so I've color-coded our inequalities. We'll graph both of them in the same coordinate plane here, okay? So choose the color red. Y is greater than or equal to 2x minus 3. The boundary line for that would have a y-intercept at -3. It would have a slope of 2. So we're going to rise 2. We're going to run 1 to the right. And we're going to keep on doing that. Fill up the grid that you're given. And should this be a solid or a dashed boundary line? Solid. Now, remember, solid just means the points on the line itself are solutions to that particular inequality, right? All right, and then I'll use the test point of the origin to decide where to shade. So plugging 0 in for x and 0 in for y, that's going to simplify to 0 is greater than or equal to -3, which is true, right? So which side do I shade? The left side of the line or the right side? The left side, the side that has the origin, okay? Now don't get crazy with your shading here because we still have a whole nother inequality to graph. Okay? All right, switch to blue. X plus y less than 2, that's in standard form. Remember, in standard form, you could just graph with x and y intercepts, which in this case are both 2. And you can see the slope between those 2 points. It's up 2, left 2, which is going to reduce down to a slope of -1. You just use that to find some more points. Solid or dashed boundary line? Dashed. So the points of this boundary line are not actually included in that inequality solution set. Use the origin again. Plugging 0 in for x and y leads me to 0 is less than 2, which is true, right? So the origin is a solution to that inequality as well. So I would say, do I shade, let's call it below or above the boundary line? Yeah, below. Okay. And we are now looking for the overlap of red and blue regions, right? Which would be this section in here. And this is what I'm going to fill in a little bit better. All right, provide the coordinates of a point in the solution set. I put this in here because Delta Math, the pre-made problems they have with regards to inequalities, they ask for this second part as well. Sometimes students think that they need to give the intersection point between the two boundary lines. Well, understand that would not be a solution in this case. Right? This point right here is not a solution to the overall system because of the fact that the one boundary line is dashed, right? So instead, we just need to pick some random point that's in the green shaded region. Okay? There's an infinite amount of answers you could give here, but just pick something in the shaded region. So I would just say the origin. Okay? Any questions on that? All right. Moving forward, example 2 is a system of inequalities with a linear and an absolute value inequality. So let's start with the linear in red. Y-intercepts 2, slopes 1/2, so rise 1, run 2. Solid or dashed? Okay. All right, now test point of the origin is going to lead me to 0 is greater than or equal to -2, which is true, so I'd shade above that boundary line. Okay, so the next inequality, it's a two-variable absolute value inequality. Require two-variable absolute value equations. What do those graphs look like? They're not lines, they're V's, right? Which have a vertex to them. What would the coordinates of this vertex be? Be careful. Evan had it right. 1, 3. So we take the opposite of the value that's in with x to give us +1, and then the number that's being added at the end, that gives you the y coordinate of that vertex, okay? So let's plot that point, 1, 3. And then the -2 that's out in front and multiplying the absolute value, that tells you two things. It tells you which way it opens, up or down, and then it tells you how steep each side of the V is, right? So the fact that that's a -2, remember that means the V's opening down. So from this vertex, let's go down 2, right 1, or down 2, left 1, and just repeat the process. Now, would this be solid or dashed V? Okay. All right, now let me show the work for the test point on this. So I could use the origin. I'd say that the origin is just inside the V, right? 0 is less than -2 times the absolute value of 0 minus 1 added with 3. 0 minus 1 is -1, the absolute value of which is 1. 1 times -2 is -2. Add that with 3, end up with 1. Is 0 less than 1? Absolutely. So that means I would shade inside the V. And where would my overlap be? In this triangular region. Any questions there? All right, now, once again, I could ask you name a point that's in the solution set. Just pick something inside the triangle, right? Okay, example 3. At first glance, you might say, oh, that's going to be pretty similar to the previous one. But notice the second inequality here only has one variable in it, not two. So that's going to change things a little bit, okay? The first one is a linear inequality, though. That's no different than the last couple examples. It's got a y-intercept of 1. Slope is -1, so let's go up 1, left 1. Keep doing it. Or down 1, right 1. Solid or dashed? Solid, right? Origin would lead you to 0 is less than or equal to 1. That's true, right? So we're shading here. The side that has the origin. Okay, for the absolute value inequality, it only has one variable to it this time, not two. So that means you're not going to get a v, okay? Instead, this takes us back a couple units. We have to recall that a one variable absolute value inequality can actually be rewritten as a compound inequality, okay? So that has two cases to it, right? So the first case would be x plus 1 is less than 3. What word should follow that? And. Remember, the absolute value is less than 3. Think of less than as less and. And then my second case would be x plus 1 is greater than -3, right? Solving those separately, I'll end up with x is less than 2 and x is greater than -4. Everybody okay with that? That's a good review of the one variable inequalities. Okay, so now the question becomes, well, how do you graph something like that in a 2D plane? Okay, well, think, if that were x equals 2, what would that graph look like? X equals 2. It would be a vertical line, and same with x equals -4, right? So the only difference is we just make them dashed lines now. I need a dashed vertical line right here. And I need another one right here. So we're looking for all the points whose x coordinates are less than 2 but greater than -4. Wouldn't that be all the points in between those two lines? And now you can see your overlap is this region right here. What if that inequality had been the absolute value of y plus 1 is less than 3? It would just be horizontal lines at -2, or I'm sorry, at -4 and +2, right? Other than that, nothing changes. All right, one final example. And this is going to kind of lead us into what we are going to do with linear programming, okay? So this says, find the coordinates of the vertices formed by the following system. Okay, so it looks like there's 3 inequalities, but technically there's going to be 5 boundary lines here. Okay, so the first is a linear inequality in standard form. It's got an x-intercept at 6 and a y-intercept at 5. Okay. And that should be a solid boundary line. Oops. Okay. Test point of the origin would lead me to 0 is less than or equal to 30. Definitely a true statement. So for that, I would shade below. Second inequality, y is between 0 and 3. So I'm looking for all ordered pairs whose y coordinates fit that criteria. So this is where you'd get two horizontal lines, right? You'd have one right here on the x-axis, and you'd have one right here. And you'd shade in between, right? And then lastly, we have x between 0 and 4. So we're going to get two vertical boundary lines, one on the y-axis and one right here. And we'd shade in between. Okay, so the solution to the system would be where red, blue, and green all overlap, right? Which, wouldn't that be this section? So what we want are the coordinates of the vertices of this region that has been formed. So we want coordinates of this point, this point, this point, this one, and this one. Okay, so I'd say three of those are really easy to find. One of them's the origin, right? Another one is at 0, 3. And then another one is at 4, 0. Okay? Now, how about this one right here? X coordinate of that is definitely what? X equals 4. Y coordinate? Kind of tough to tell just by looking at it, right? So how can we be certain of the coordinates of that, of the y coordinate of that intersection point? Yeah.
We could put 4 for x into the first equation.
Right. So we know the x coordinate is 4, and that point is the intersection between the line x equals 4 and the line 5x plus 6y equals 30, right? So it's like we're solving the system of equations that's creating that intersection point, right? So if I had 5 times 4 plus 6y equals 30, that's going to be 6y equals 10, or y equals 10 over 6, which reduces to 5 over 3. So that has exact coordinates of 4, 5 over 3. Questions on that? Okay, and then our final point would be this one right here. That's the intersection between the horizontal line, y equals 3, and then that same red line there. So y coordinate is definitely 3. And couldn't we find the x coordinate the same way we just did with the other point? So now it would be 5x plus 6 times 3 equals 30. 5x plus 18 equals 30, or 5x equals 12, x equals 12 fifths. And here's what we're working towards. With the process of linear programming, we're going to take those vertices and we're going to plug them into what's called an objective function. And ultimately, we're going to see which of those vertices leads us to the largest value and the smallest value in that objective function. So that's what we'll do at the end of class here. Okay?